Alright, today I will talk about some space-time diagram, which is there's some diagrams for the spatial relativity theory. The content on the graph and some processes, some formulas coming from the theoretical minimum, which is written by the Leonard Susskind. Now, thoughts. I want to mention that the points of the spatial relativity theory is some unified space-time to satisfy the some invariance quantity. I mean, the some covariance for the electromagnetism, which is a Maxwell's equation. But in this video, I will only focus on the some space-time diagrams to explain about some relativities of the space and times for the each observers in prime. So first of all, there are some of the internal relativity with the Galilean transformations in the space-time diagram, X and T. And there are the two possible primes, which is observers in the last prime. So just X is equal to the 0. And the moving observer prime X equal to the VT. And there's a relationship between the space and time for each prime. There's X prime, which is the moving prime. The T primes are equal to the X minus VD and the T respectively. And it can be expressed in the space-time diagram like that. There are some specific events at the point X prime T. For the last prime, that is just the X comma T, but the for the moving prime, there are specific points on the lines of the X equal to the VT. So for that observer, such events as observed as X prime and T prime, which is X minus VT prime T. But in a spatial relativity theory, there are very some different behaviors because of the Lorentz transformations. So Lorentz transformations coming from the some covariance invariance so for the electromagnetism. And the space-time diagrams changes like that. There are some of the X and the T for the last prime observer. And the for the moving observer, the X prime axis and T prime axis is given like that in the spatial relativity theory, space-time diagram. And for the moving observers, X prime and the T prime, X prime equal to the G's and T prime equal to the G's axis are given like that. And there will be the X equals the CT, which is the like. And we will set the is equal to the 1 light speed, and the light cones has a 45 degree. That is not the regimes of the spatial relativity theories with the space-time diagram, and I will explain what the Lorentz transformations in the maybe this next video. There are some specific phenomena in the related with such as space-time diagram in spatial relativity theory. The first one is the relativity of the simultaneity. So there was some other primes are same for the previous figure, but there will be some specific events. Event at the point O, which is origin, and the point A and the point B. So the situation is given like that. So there will be some light will be emitted at the point event point O and event point B, and there will be the light will be the reaches at the some event point A, and for the primes of the moving observer, the time of the event U and event V is the same. So it represented like that. The light will be the going to the path of the 45 degrees because we said already this is equal, and the 45 degrees from the B to the I. That was about the moving frames. So O and the B has the same time for the moving frames observer. But in the case of the last frame observer, O and the B is different because in this axis, which is just the T axis, the times of the event B and the times event O is different. So the time of the event B. So that is called the relativity of the simultaneity for the two different events. So the simultaneity will be different for the each observer's in the plane. So that is not the relativity I already explained, and we can assign this algebraic relation for that this line in the space-time diagrams with this very simple elementary algebra, just a linear line. So so first of all, we can bound the point A as a intersections of the two lines. The line runs this x equal to the CT, and we will start the point A is positions at the distance L. So OI has some distance L and IB has distance L. So there will be some I, 0 points. And for the moving frames, that will be the moving in the velocity in V. So the path will be becomes like that. So for these observers at I, observers, the path will be represented in this line in space-time diagrams, and they can be represented in linear equations in the space-time. And by the binding of the intersection points of these two lines in space-time diagram with the simple algebra, then we can even find this what is this point i's in the space-time diagram. So from that, let's starting that the t is equal to the x minus l over the v is equal to the x over the c, then we can bound sort of the x and the t of the events I in the space-time diagram. And the next step is the bounding of the point B as intersections of this line, which is the A is lies on in this line, and the angles of this line is the 135 degree because of the 45 degrees for this as a light cone. And the from the B will be started in the 2-hour distance at the time t equal to the 0, and it removes it in the velocity in the V. So such a path of the B can be represented in space-time diagram with this equation. And such a 45 degrees light path can be represented like that. So from the bounding of the cross intersection points of these two linear relations, solving of the such a equation, then we can find the event B in the space-time diagrams with the time t and x. And there will be some dependence of the velocity v and this distance r. And yeah, so also we can starting the c is equal to the 1, but I just like this is in the formula. So from the so we can bound through say point B here. And the both its moving primes, the O and the B should be the same time. So we can boundary the x prime axis by the point B in this space-time diagram. And we know that the x and the t recognized both the point B. So x prime axis is given like that, t equal to the v is over the c squared with x, and if we set the c is equal to the 1, then the t is just the vx. And similarly, we can bound up the t prime, that is just x equals to vt from the classical regimes of the Galilean transformation. So from that, there are symmetry between the spacer axis and time axis with moving from. So x equal to vt and the t equal to vx, and I said the c is equal to 1. So in the spatial relativity theory, there will be some contractions rotating the axis with the time axis and the spacer axis. There are some of the geometrical views of the Lorentz boosts as a rotation of the time axis and the position axis. And then maybe the next videos I will explain about the Lorentz boost very detail. And I will mention the very briefly about some space-time integration in here. Maybe the derivation of the Lorentz boost will be missing in this video. There are some just widgets of the Lorentz boost. X prime and the T prime for the moving prime. And we define that the gammas equal to the 1 over the 1 minus the v squared to the c squared roots. And the badass is just v over the c. And that is the Lorentz boost. And Lorentz boost can be interpreted as some rotations with the imaginary angle. So cosine I set as equal to the cosine hypercosine set as and sine I set as equal to this hypersine setup. And we set the cosine hyper set as equal to the gamma and the beta gamma, and it satisfies that the such relations of the hyperbolic trigonometric functions. That is some starting of the gamma and beta. And the meaning of the Lorentz boost, the point is the Lorentz boost is the rotations of the times on the spatial axis with the imaginary angle. So geometrical views of the space-time diagrams we already showed in the previous page. And from the imaginary angle, we can study that the some invariant space-time interval. So r squares equal to the x squares minus t squares, and there is invariance under such Lorentz transformations with the prime notations for the x and t. And if we studying that the imaginary time t equal to the ICT, and the x squares and t squares are invariant space-time interval, it can be interpreted as such rotations within sort of the spatial axis and time axis. And such derivations of the Lorentz boost will be discussed in the maybe the next videos. And I think there are some of the some redundant things and some very not good qualities about some captures the images and some formula derivations and some of the not summarized words in here. So I'm sorry about that. And maybe this next videos I will discuss about some derivations of the Lorentz boost and the phenomena of the time dilation and the length contractions of the spatial relativity theory.